This video will help you with problems that can be solved by realizing that the center of mass is remaining stationary in the problem because there are no outside forces acting on the system. The classic example of this is a raft in water with a person at one end and the person walks across the raft. This is the type of problem that's in both the AP review packet and in the homework in the textbook. There are other ways this problem could be framed, could be set up, and I'll give you a general method that would help with any other way that you could set it up, but this is the most common way. And it has the unrealistic idea that there's no friction between the raft and the water, which of course is completely wrong. There's maybe we shouldn't call it friction, but there's definitely resistance from the water. So this would never happen in real life. However, you could simulate it more or less by putting the raft on very slippery ice, or make the raft, instead of a raft, like a hovercraft type thing. So if it's hovering on a cushion of air, this would be closer to being true. And I actually have a demonstration where I do this with a board on rollers under it, and that shows you the effect. Okay, so this is the situation. Very large raft and a person. The raft is in water, and we pretend there's no friction, no resistance, and the system has no outside forces on it. And the system consists of the person and the raft. The person walks to the right. They're pushing, in order to walk, they're pushing on the raft to the left, so the raft moves to the left as they walk, as the person walks. And the question will be, you see that the raft has moved. If they give you the mass of each and how long the raft is, so you get the mass of the person, the mass of the raft, and the length of the raft, and the person walks from one end to the other, how far has the raft moved in this direction? That's the way the problem is framed in its classic sense. So here it is with specific numbers. This isn't a person now, it's a car. Like I have a toy car, I put it on a board that's on a friction-free surface, like say a very slippery ice, or I put it on rollers. The car starts here. There are no outside forces acting on this. The car moves to the right, so the car starts here, but then it starts to move like this, and at some time later it's reached the other end of the board, the raft, we'll call it, the raft, and because the car is pushing left on the raft and the raft is pushing right on the car by Newton's third law, the raft also moves because there's nothing to keep it in place. There are no outside forces to keep it in place. So the raft moves this way. And clearly, if the raft is big, it has more inertia, and the car has less inertia, the car will move further from here to here than the raft does, the center of the raft moving from here to here. Okay, and the question will be, how far did the raft move? I encourage you to just try to figure this out on your own. It's possible to figure out, and there are multiple ways to do it. But I'll give you one method, and this method could also be used for any problem where you have no outside forces on a system and the center of mass stays in one place, and then you're asked questions about the system. So here's my method. Pick up this diagram here in the initial picture and put it on an x-axis. And what that really means is the reverse. You would take the diagram and draw an x-axis through this. Okay? And establish where the center of mass is from the givens. And there's enough information here, 2 and 10 kilograms and 36 meters, that you can figure out where in this picture the center of mass would be. That's easier for you to do if you draw an x-axis on the picture. So, for example, in this particular picture, I would do this. X, and where am I going to make my 0? Well, of course, we want it to be positive numbers, and the 0, the most obvious place, will be right here. This would be the 0 mark. Since this is 36 meters long, this would be the 36 meter mark. And that can help organize your thinking about this system. Since there are no outside forces, the center of mass does not change, XUM. Center of mass does not change. Figure out where it is, and then no matter what happens, like it'll be a number on the x-axis. Figure out what that number is, and then no matter what else happens to the system, that will always be the same place. That center of mass will always be in that location at that number. So all else follows. Everything else follows from that once you've found the location of the center of mass. Okay, I'm not going to do that problem. I do an example with stars, and I think after the whole video you can figure out why I do this example. Okay, here are a couple of stars, 2 kilograms and 3 kilograms. They're 10 meters apart. I'm not an astronomer or an astrophysicist, but I don't think these numbers are realistic, a 2 kilogram star and a 3 kilogram star 10 meters apart, but they're easy to work with. So as I said, put an x-axis on the diagram. 2 kilogram here, 3 kilogram there, 10 meters apart, so that means these are now defined as locations. this has a location x equals 0, and that's x equals 10 meters. And then the problem is going to be something like, what if they're rotating? Like if this is a binary star system and they're rotating around each other, and you look at it sometime later when they've switched positions, and the 2 is on this side and the 3 is on that side. Or perhaps they're going to collide and they're going like this. And you look at it later when they're 5 meters apart and you want to know where they are. And one simple way to do that is to identify the location of the center of mass and mark it and then go from there. The center of mass cannot change. These 2 stars are the only things in the neighborhood. Nothing else is exerting a force on them, so their center of mass must stay the same. So let's figure out center of mass. You might be rusty on this because it's been since the beginning of the chapter, but if you need to, you can look it up. You get the center of mass is at the 6 meter mark. So I put a mark there, off center, right, at the 6 meter mark. And I note a few things. This is 6 meters from here to here, from the small one to the center of mass, and as we would expect, the distance from the center of mass to the bigger one is shorter. And you can do a quick check. Notice mass times distance equals mass times distance. This is like a balance point. And the moment arm of this, mass times distance equals the moment arm of this, mass times its radial distance. So you notice that can help you do these problems faster. I'm doing it in a very computational way, like a computer would be programmed, but if you do this with insight, you can go a lot faster. All right, so here's the problem. The stars rotate so that they've switched their locations, and the bigger one's on the left. Where are they? Okay, they don't just switch like this. That's impossible. They don't switch their exact locations because then the center of mass would move. And there's no outside force, so the center of mass cannot move. And if they switch their exact locations, and you think the center mass is still here, that's impossible because then the smaller one is closer to the center mass. Not possible. Okay, so they switch their locations, and the question becomes, where are they on the x-axis? Okay, so here's how to do it. The key idea is that the center of mass does not move. And we've established that the center of mass is at the 6 meter mark. So let's put 6 meter mark. That's the center of mass, x center of mass. That cannot change. And what they've done is they've switched positions now. So I'll make a little mark up here over what they look like. Up here I'll make a diagram of what they look like now. They've switched positions. So now the 3 is on the left and the 2 is on the right, but they're still 10 meters apart. Right? So I'll mark that with my green. There's still 10 meters between them. So what I have to do is arrange a 3 on the left of the center mass and a 2 on the right so that 2 things are true. They're 10 meters apart and the center mass is still at that location 6, because no matter what they do as they rotate around, even if they get closer or farther apart, the center of mass will always be at x equals 6. Okay, so let's see, that means I want to put the 3 on this side and the 2 on this side, so ask yourself, which one should I draw closer? Okay, and of course you should draw the 3 closer. 3 kilograms on this side, and the 2 kilograms, I'll exaggerate it, farther away. Okay, this is not a difficult problem to figure out. This distance, it can't be done, of course, unless you know this is 10 meters. Okay, so you have to find where this would be and where that would be so that they're 10 meters apart, but also so that you get a center mass of 6. And for this type of simple problem where all they've done is switch places, it's easy to go back to your original picture and look here and see, oh, duh, the smaller one has to be 6 meters away from the center of mass, and the bigger one has to be 4 meters away, and then you just take that and write the same numbers in. Okay? So the smaller one has to be 6 meters away, and the bigger one has to be 4 meters away. So this is 6 for the location of the center mass plus 6 more. So this has to be at the 12 meter mark. And this is at the 2 meter mark. So that answers our question now where they were. Remember, they used to be at 0 and 10, but now when they've rotated around, this is now at 2 and this is at 12, and it maintains the same center mass, which cannot move. You could go through and set up an algebra equation to do that, but I think it's easier if all they've done is switch positions. It's much easier just to look at your previous diagram and look at what these radial distances were, and then just switch the radial distances, and you'll keep the same center of mass. You have to be very careful with all this. It's really easy to make the mistake of thinking they just exchange positions. That would be completely wrong. It starts from identifying where the center of mass is and then making everything else revolve around that, pun intended, Everything else revolve around that so that you never change the location of that center of mass. Okay? Now, let's look at a different type of problem I could ask. This would be not rotating stars, but colliding stars. The stars began 10 meters apart like this. So this is the same initial diagram you saw before. Smaller one here, larger one there. They start here, and this time instead of rotating and changing their orientation left and right, they're attracted and they're getting closer to each other. They're colliding. These two are not spinning. They're not revolving around something. They're moving towards each other. This is a colliding star system. So you look at some later time, final position, they're closer together. Instead of being 10 meters apart, they're now 5 meters apart, and we ask, where are they? Once again, make an x-axis, and the whole thing starts with the center of mass being at 6. There are no exterior forces on this, so the center of mass cannot be in any other location other than the 6 meter mark. Okay, so now a couple of things have to be true here. The 3 is on the, I've drawn these backwards. Final positions, I switched them. Okay, so I didn't mean to switch them. I meant to write the 2 there and the 3 there. There we go. So I was saying they don't switch position. They don't switch position, they just get closer together. Okay, so they're 5 meters apart, and the 2 is on the left and the 3 is on the right. Which one should I draw closer to the center of mass? Of course, the 3. So that's 3. And which one should I draw farther away? The 2. So exaggerate, 2. And this distance between them is 5. That distance is 5 meters. I just want to know what these distances are. I want to know where they are. Okay, so I think the easiest thing to do is to call this length d, right, from here to here. From the 2 to the center of mass, you call d, and the other distance, what would that be? Well, if the whole distance is what, and this is d, what are you going to call that? And the answer, of course, is 5 minus d. And now you set up your center of mass balance equation, right? That the mass times the distance to the left has to equal the mass times the distance to the right. You could set up the formal center of mass equation, 6 equals, and write it all out, but I think just some common sense makes sense here. Center of mass is a balance point, so 2 times d equals 3 times 5 minus d. And of course you get 2d equals 15 minus 3d, and eventually get d equals 3 meters. So that tells you where they are. If I'm going to draw this, I have the 2, I have the 3, I have the center of mass here at 6, and then this is 3 meters, so this must be the 3 meter mark. And what does that remain? What remains here? What distance does that have to be? That has to be 2 meters, and so this will be the 8 meter mark. And that answers the question where they are. The advantage of doing it this way instead of just using common sense is if the numbers are trickier. If this is 2.8 and that's 3.5, and the distance between them is 11.6 meters and so forth, and then they're closer, they're like 1.2 meters apart, the same process will give you all the answers. Here it's pretty obvious. I picked really easy numbers, so it all makes sense when we're done. But the same process will work no matter how tricky the numbers are. Finally, let's look back at the original problem. Well, the original problem looks trickier because there aren't dots. But that's okay. Remember, the day we did center of mass, we said you can take any uniform object of uniform density and reduce it to a single dot at its center. And that's what we're going to do. The default on these problems is that the objects have uniform density. So if a car starts on the left, we consider it starting exactly at the end of the raft. The raft has uniform density. The car or person has uniform density. Remember, the problem is the person walks or car goes to this side. How far did the raft move? Uniform density means we can represent each by a dot. So we start with this 2 kilogram dot here. This is the initial. Start with a 2 kilogram dot here. And where should we put the dot for the raft? Over here at x equals 36? No, because all of the mass isn't here. It isn't here. Right in the middle, you represent the raft by a dot at the exact middle, which means that 10 kilogram dot goes here, not at the end of the raft, not at the left side, but here. So what would this distance be? from the end to the middle, and of course it's 18 meters. Okay, then you do it like the previous example. Now you have two dots. It's exactly like the previous example. Two dots, you know the mass of each. You have the distance between them. You can find the center of mass and go from there. I got the problem started. I'm not going to finish it. We define the leftmost point as our x equals 0. This is the center of the raft, remember, not the end. And that creates a center of mass here, which is easy to calculate. This is 3 meters from the end. The smaller car is 15 meters from the end. And then the car goes, they basically switch their positions. The raft moves left, the car moves right. How do I know they switch? Because the center of mass can't change. So the raft moves over here, the car moves all the way to the end. They're still 18 meters apart, so basically they switch. So I know that the center of the raft went from here, 3 meters to the right of XCOM, over to here, 3 meters to the left of XCOM. And that's why very quickly I can do this. But if you had to go through more steps as I did on the previous page, you can do that. Here is the final answer. You should try this problem and make sure you can get the exact same answer I did, whether it's by cranking it out or by insight and understanding.